Thank you very much for the intro. Thanks everyone for sticking around for the very last session. So yeah, we want to talk about AutoML in the age of structured foundation models, which means, we have AutoGluon, we have tabular foundation models. How do they interact? And well, first, to set the tone, you should, if there's one thing you take away, deep learning has finally cracked tabular data after many years. It finally excels, and all of these methods have been published within the last year. A different view, all of these methods have been published in the last year. They do outperform the traditional methods, and that changes the landscape. And what should we do in order to get the best out of this? So first, I will talk about tabular foundation models to set the scene, where is this great performance coming from? And then Nick's going to talk about benchmarking in the age of tabular foundation models and Tabarina. And then I'm going to do a quick demo of TabFN, what you can do just to see that you can really interactively use it, like gradient boosting and so on. All right, for my part, for my talk part, there's three different parts. There's first, motivation. Why do we actually care about tabular foundation models other than they give us great performance? Then the in-context learning part of TabFN, TabFN-v2, and then some on extensions of that work. All right, let's get started with the motivation. So first, let me set the scene. What is tabular data? Just to make sure we're all talking about the same thing. It's a age-old problem that you've seen in Machine Learning 101. Like you have some, you see them? You don't see the mouse? Good. You have some columns of data here. Then you have a Y column. That's a particular column you want to predict. There's training data and there's test data, and the test data here you want to predict the Y. So this is X train, Y train, X test, and Y test is what you want to predict. All right. There's a lot of other examples, also very relevant in different business contexts, like will a customer churn, or will a person buy a product, or will the credit be paid back, or in medicine, will this treatment help this patient, etc., etc. Tabular data is ubiquitous. There's literally thousands and tens of thousands of use cases in all kinds of different verticals. And closely related, there's also time series forecasting, where you might want to, given a time series like this, you want to forecast the future stock prices, energy prices, solar energy production in order to do cool things, etc., etc. So why do we want foundation models for that, other than the great performance? Well, with traditional ML, for every data set, you have to start new, and that leads to individual siloed models. It's sort of this lengthy task-specific training. And in contrast, for foundation models, we have a lot of data sets. We have one costly pre-training phase, but then we can use the model out of the box without the costly training phase. And you can also use similar data sets from your domain and fine-tune it to these data sets and just get better performance that way, and really exploit. If you have a deep learning model, then you can exploit other modalities, do joint fine-tuning, etc. And it just plays much nicer with the deep learning ecosystem. All right, why did deep learning not crack tabular data much earlier? Well, one thing is you have heterogeneous data. So you have columns can be categorical or numerical or ordinal. They can also contain text. There's outliers, imbalance in your data. Then you have input features that are already high level. So they are created by humans. Like, I don't know, for this banking data, this is the customer's age and this is their income. And so there are high level features, which is very different than text. There's just a word, or then especially vision, there's just pixels. Individual pixels have almost zero information, and you really need this deep learning, representation learning to learn different layers of the representation on different layers of abstraction. And then in the top layer of the neural network, you have learned this great representation, and then you have learned it such that just a logistic layer in the end is actually enough. That's where we start with tabular data. So we don't need another deep learning phase necessarily on top of that in order to extract these features. And that's really, this is where machine learning originated. This is where it was cool already like 50 years ago, before like we had successes in vision and so on, before we had deep learning. But then deep learning was particularly useful for this unstructured data in order to actually come up with these features that we already have here. Then data sets are much too small, typically for normal neural networks, so you overfit. And there's also not enough data in order to build foundation models. So humans like to put text on the internet. We're a very social species. We like to put images. We don't put our tabular data sets on the internet. Nobody cares about our tabular data sets that in a social context. And typically these contain private information and so on in the business context, and they're very much guarded. So there's not trillions of tokens that you can just get from the internet. All right, still we want these tabular foundation models. And yeah, there are a lot for text, there are a lot of images, and our amazing community shall build the ones for tables and time series and databases. All right, hopefully you're motivated. So we'll talk about TAPIFN now. All right, in a nutshell, what TAPIFN does is here on the left, we have synthetic data sets, X-train, Y-train, X-test, Y-test. The Y-test we take out. This part here with a question mark, we feed to the TAPIFN. That's just a neural network parameterized by some parameters, and that should output a probability distribution for the Y-test data points. If there's multiple data points, then it should output multiple of these distributions. And then you just look at the negative cross entropy between the Y-test and the predicted Y-test. And that is your error signal. You backprop on that. And that is like for one data set, you push this through and backprop once. And then you sample another data set and you do this backprop again. And you sample another backprop data set and so on and so on. And we do this like 130 million times with 130 million different data sets that are sampled from some distribution. So we basically, we have a synthetic data generator, so we can generate arbitrary amounts of data, similar to the trillions of tokens for a language on the internet. And if these data sets come from a distribution that is very similar to the distribution of the real data sets that we care about, then the magic of transformers and modern deep learning makes it such that the parameters of the network help us actually get an output distribution that very much minimizes this cross entropy here, and therefore give us well-calibrated predictions. Like just given the X-train, Y-train, X-test, there is uncertainty. We don't know exactly what should be the Y-test, so we need to make probabilistic predictions, and we need to be properly calibrated. All right, crossing my fingers there. All right, moving the slides does not help. Let me see. I did not do anything. My computer is still there. Just have to be nice to it, not touch it. All right. I shall stay away from it and use this. All right. So this here is on the synthetic data. So this is a pre-training phase, and there isn't a single real data set there. This is all synthetically generated. And if we can do this, like predict the Y-test, for a lot of data sets, then we can do so for a real data set where it's actually missing. There we then predicted in a forward pass, we predict a distribution, and hopefully that actually matches the right distribution. Now there's two details. One is what's this neural network? Different architectures will help to do this task better. And the even more crucial one is what is this prior? We actually want to have a prior that mimics the type of data that we expect. Theoretically, what we will do with a TAPIFN is a particular PFN, which is a prior fitted network. And we read this paper in 2021. Transformers can do Bayesian inference. So that showed that in this transformer, in a PFN, we actually compute the Bayesian posterior for a given prior. So whatever the prior we give, we compute the Bayesian posterior for it. If the prior is linear lines, we'll compute Bayesian linear regression. That's not going to be helpful if the data is quadratic. So we do need to think about what should the prior be. We could like take arbitrary priors, anything in the universe, and it's probably also not going to be useful. So it needs to be sort of mimic the type of data that we expect. All right, architecture first and then prior. So the architecture in WFNV2 is as follows. So this here is this picture here with a question mark. So this question mark here is what we want to predict. And we basically just have 12 layers of a transformer. There's an embedding for each of these. And then we just have an embedding for each of these elements in the matrix. And then we do one attention over the features, and then one attention over the samples, and then a standard MLP that's for each of the elements here. And after 12 layers, we take the final MLP for this value here on the output and actually transform that into a piecewise Riemannian distribution. So it's this binning distribution where we bin the output space, and that gives us these multivariate output distributions. So if we actually have a case where for a data point, the Y value might be on the left or it might be on the right, but it's very unlikely to be in the middle. With a Gaussian output, we couldn't fit that, but with a multivariate, we can. All right. That was architecture. Now the prior. So here we integrated principles from causality. We thought, hey, what would tabular data typically look like? Probably there's some types of causal relationships in the data. There might also be independence, but some of the features might be correlated. So what we do is we actually sample and initialize structural causal models. We take a causal graph, sample edges in this graph, sample where will the Y values, where will the X values be in that graph? And there's going to be latents as well. And then also sample connection strings and activation functions and so on. And then there's these input nodes, here denoted as epsilon. And so you can think of this structural causal model now denoting a function, a data set, and then we can sample data points from this data set by instantiating the inputs of the structural causal model. So here we have like 3 different inputs, different random values for these inputs, and we just push them through the deterministic structural causal model. This is actually a PyTorch graph that we can push it through. And then we just read off, okay, this here is 0.35. That's supposed to be the Y value. So we take this is going to be the Y value. This is supposed to be X1. That's supposed to be X2. We have sampled the data point and like 2 more data points here. This would be for regression. If it's classification here, binary classification, then we just need to sample a threshold, and then we sample a Y and 2 other Ys. All right, so we sampled a data set with 3 data points. And in practice, we're going to sample 100 million data sets with like 1,000 or 2,000 data points. And then we also have in that prior a simplicity principle that says it's more likely to have simple functions than complex functions. So simple functions like these are more likely than complex functions with these, with lots of latent structures and so on. This is possible, but in the absence of the need for it, we want to actually make simple predictions. That's very, very much the Bayesian Occam's razor. All right. So we sample data sets. Here on the left, there's 2 synthetic data sets. On the right, there's 2 actual data sets. All that this is meant to show is I can't tell these apart. They sort of look real. We don't have any concrete numerical estimates or distributional estimates on how similar they are. We also don't want to overfit too much, but eyeballing it, it sort of looks like you could learn something from this. And then that's what we need. And basically, if you learn a method that for some of these data sets, or for millions of these data sets, if you label some of them X train, some of them X test, you can learn to interpolate in the space, then you've learned a classifier, and that classifier can be used for new data sets. And that classifier actually then, because you try to actually yield because you train it with cross entropy loss, you don't want to make predictions that are wrong and you're certain about them. That's the worst that can happen for cross entropy. So if you're actually uncertain, or if you might be wrong, then you rather want to say my uncertainty is high, and this is actually what happens automatically. So here there's this simple toy data sets from scikit-learn, this half-moon data set here, and you see the decision surfaces from all the different types of methods. We see CatBoost, for example, is just a very tree-based model, very axis-aligned. TAPIFN is just very smooth and away from the data, it makes reasonable uncertainty estimates. All right. Another qualitative results is it's very flexible and good in its uncertainty quantification. For example, here in this data, there's just some missing values, and you're tasked to predict in between, and it can predict, here this is the noise, and here this is heteroscedastic noise, and it also predicts that the noise would be growing there. In contrast to previous MLPs, we can quite nicely fit what could MLPs not fit? Of course, step functions. That's quite problematic. TAPIFN isn't perfect, but so that's something that CatBoost is of course great at. But CatBoost is very bad at actually having true sinusoidals or quadratics or anything like that. That's just very much a point estimate for these tree-based methods. All right. And the third qualitative result is these multimodal predictions. So this was published in Nature. We wanted this sort of experiment that appeals to real scientists. So we took this duality of light being a wave or particle, and this double slit experiment where light passes through the slit, and then you get this interference pattern on the wall. And that's what this looks like. So for each X value, you have this multimodal distribution where there's a peak here, this is the biggest peak, and then they sort of get lower. And CatBoost can't do this very well, but TAPIFN can actually do this, in this case, with the binning distribution, which just have 5 peaks. All right, this is not to annoy the AutoML community, but to sort of wake us up a little bit. We need to have methods that are simple to use, and AutoSQL is something that I really love. It's been very fundamental for this community, but it is complex, and people don't like this complexity in practice. It has been used a lot, but it would be used even much more if it's just a forward pass. A forward pass, is something that you can put into hardware on a sensor. You can put this in Onyx, and then you have a machine learning algorithm that's running on a sensor. That's different than having a complex beast with a lot of pre-processing, assembling, and whatnot. So that is something that in some applications is crucial. In other applications, it sort of doesn't matter. It's a black box somewhere, and you call it. But that is something that some people, data scientists, really like. This type of interface much more than the interface where they need to wait over the weekend. All right, quantitatively, and AutoML will of course come back, and assembling will kill this, and so we can all go home happily. But so quantitatively, it has worked really nicely. So we have linear regression MLPs, SVMs, random forest, and then 3 different gradient boosting methods, LightGBM, CatBoost, and XGBoost, all in the default are tuned for 4 hours with random search, as is a community standard, sadly. But that was the one that was the least attackable. But had we optimized this with Bayesian optimization, it wouldn't look much different. And so even if you tune it for 4 hours, it doesn't get anywhere close to where TAPIFN is after 5 seconds. And that was very surprising to us, and quite cool. This is a result that holds on average. It doesn't hold for every single data set. There's one data set, for example, here where CatBoost in the default is actually better than TAPIFN. But on average, on most data sets, it is better. And so here's another view of this. So after 5 seconds, you're already better than all the other methods, and you keep tuning them. For regression, there's sort of similar results. They're not quite as strong. And then we put in AutoML from AutoGluon, we put in post-hoc assembling, and that was actually really crucial for regression. For classification, even the default TAPIFN here was already as good as AutoGluon after 4 hours. This was, of course, the AutoGluon version back then, which I think was 1.2. For regression, Actually, the PHE, the post hoc assembling, was much more important in the tuning. There, the default is not as good as AutoGluon. But with tuning, so hyperparameter optimization, you're sort of similar. But with a PHE on top, it was actually better than AutoGluon assembling, all kinds of other methods. All right, yeah, then a bunch of ablations. TAPFN is now in version 2 robust against uninformed features. It was not in version 1. So here the setup was adding, for one feature, adding 9 times a feature just as noise. And that completely screws up MLPs. But and screwed up TAPFN v1. But in v2, we just told it in the prior, there might be uninformative features, and then it just didn't care. It just learned not to care. Likewise, there's missing values. In the prior, there were some missing values, and then it's like, okay, there's missing values, whatever. Categorical features, we put a lot of effort in putting them in the prior, and now they're also fine. That was also an issue in v1. And yeah, one nice thing is that it's really quite strong with less samples already. So with 50% of the samples, it's as good as CatBoost with 100% of the samples. So if you have a patient study and you need 5,000 people in your cohort instead of 10,000 people, well, that saves a lot of money and maybe ethical. Yeah, it's more ethical to use less people in your patient study and so on. So that is, of course, very helpful. All right, then this is a foundation model. It has foundation model capabilities. You can fine tune it. So for example, on the right here, we just have these orange data points. They come from this yellow curve, which is a sinusoidal, but it doesn't know that it comes from the sinusoidal. And it doesn't do so well. So in blue are the predictions. But if you then fine tune TAPFN on a few sinusoidals, it actually makes much better predictions that are not perfect. So you see the blue is deviating from the yellow sometimes, but it's just dramatically better, just like if you fine-tune your llama to your data. Yeah, you can use it for density estimation of different data points just by writing density estimation as basically the predictive probabilities of the individual x's given the previous x's. You can do data generation that way, and you can also look at it as embeddings. And for example, here's a PCA on the original embeddings and a PCA on the TAPFN embeddings, and it just clusters the data points much nicer. All right, yeah, and it has had quite a lot of impact. So 250 citations, 4,000 stars, and 1.8 million downloads being used by a lot of people in the community. So that's why we care about this and why we want to put this into our solvers. All right, some extensions, what has happened since by us and by others. One thing is you can use this for time series. So you cast a time series basically as a tabular problem. So this is your history, this is the X train, basically a running index, a year, a day of the week, etc. So you featureize the data, and you can featureize the future just the same. And then you can predict just not auto-regressively, but say, hey, 17 days in the future, give me that in a forward pass. Can directly do that. And yeah, it's the same interface. And this simple trick with the model from nature that has never seen a time series in its life was actually the leading method on the GIFT-eval benchmark, which is sort of the most prominent benchmark these days for time series. It's a small model, 11 million, smaller than Chronos and TimesFM. And more importantly, it's only been trained on the synthetic tabular data, never seen any real data, never seen any time series, never seen this weird featureization of time series, and nevertheless, it will work better. And it was clear that this is not going to be the end. And you can do much better by pre-training and fine-tuning on real time series. And since then, there's many, many better models. Tyrex is currently leading, but there's like another 8 that have come out since January, and this is a booming field. So I think we have definitely not seen the end of that. All right, lots of other methods. I should have probably animated this, but so there's one issue is scaling to large data sets. I didn't mention this in too much detail. One of the limits of TAPFN of all the results I showed was for up to 10,000 data points, up to 500 features. And we want to scale this up. So we want to scale this up to larger data sets, and there's many different ways for doing that. For example, retrieval is a big enabler here. So local PFN from layer 6, Valentin Thomas there et al. They basically find the k nearest neighbors in the training set to provide a local context for TAPPFN and then fine-tune TAPPFN on those local contexts. So that's visualized here on the right. TAPDBT, also from layer 6, Jeremy and also Valentin, they iterated on this. They actually had an SSL pre-training, so not the autoregressive like pre-training of TAPPFN, but rather punching holes in your data. So that also worked very similarly. Then there's some non-foundation model works that are also sort of retrieval-like. So TAPR basically had this feed-forward net with a custom KNN component, modern NCA, sort of a neighborhood component analysis in a neural network. So there is still a lot of work in traditional deep learning, not foundation models, that is also quite strong. We'll see that that can be ensembled. Then in the Nature paper, we already had this retrieval trick of actually building like little random forests with TAPPFNs in the leaves that clearly made it better for up to 50,000 data points we evaluated. And you can also, I mentioned earlier, we can do fine tuning. Yandex also had a cool paper on fine tuning. You can also do prompt tuning, where actually, what do you actually put into the context for TAPPFN to run? You can tune, like basically make artificial data points that you would feed into your network to then do well on a large data set. And you only use a large data set for the evaluation, and you're not quadratic in that, which is linear. And of course, we can also look at more efficient architectures. We don't need to use the transformers versus standard quadratic runtime. And so it's quadratic in the context length. And what TAPFlex did is we'll just use some linear attention. So there, they also had separate specialized networks for many features, for many data points. And that makes a lot of sense because the memory can be quite annoying if you have large data sets like that are large in data points and number of features. So then that gives a lot of headaches. Having a couple of separate networks and sort of if-then statements or a router network with a mixture of experts might make a lot of sense. And Topical is a nice work from Gael's work, David Holzmüller. They learn column embeddings to represent the features distribution first. And then they also have this quadratic attention, but they only have a quadratic attention for one embedding per row, not one embedding per cell. And so they're only n squared, not n squared times m, which is actually the complexity of TAPPFN right now. And so, yeah, this is a promising architecture that does scale a fair bit higher. And they also did some curriculum learning where they started with smaller data sets. And then over time, they had like 3 different phases, trained with larger and larger data sets. And this is just very expensive. But of course, it helps to train on larger data sets. Actually, in the Nature paper, we trained up to 2,000 data points and evaluated up to 10,000 data points. If you train up to 10,000 data points, then it's going to generalize better to 10,000 data points and also to like 20 or 50,000. All right, but it is a compute question then at some point. All right, then there's lots of cool work on reducing inference time. So Andreas Müller has done great work here, in particular with this hypernetwork approach, where this architecture, you might look complicated, but in the end of the day, this is sort of a TAPPFN, this part here. And then you have this MLP that spits out not the predictions y-hat test, but actually the weights of a neural network of a simple MLP. So this network spits out the weights of another network. That's why it is a hypernetwork. And you train it by actually looking at the X-test, pushing the X-test through these weights. Some of these weights are pre-trained and some of them are adapted for each new data set. So it's, like it's a low rank parameterization. And so you can look at this, how likely is this Y-test given this X-test and X-train, Y-train? and then backprops through this whole thing in order to change all the parameters of the network and learn to output a hypernetwork that you can then apply to new data in order to get an MLP. And the MLP is just, well, given a new X test, it's blazingly fast. You just do this MLP forward pass. All right, so that was very cool work, and actually showed that it can work better than actually training an MLP from scratch, because it's regularized to actually output parameters of an MLP that don't overfit. And then a follow-up work that we did together with Andreas is also very complicated, but this is a TAPIFN with a TAPIFN v2 architecture. And basically, and in the end, actually it outputs this shape function. So it outputs a generalized additive model, which basically is just for each of the test data points columns, you have a little function. And you just look at, well, this x1, what value is that? It's 7. Let's look up by function at 7. Okay, it's this function. It's a certain value, f1 of this. And then your overall function is just a sum of these little lookups of your predicted shape functions. And then, yeah, you can compute your loss and again, backprop through this whole thing. And given a new test data point, now you just need to look at the shape functions that are predicted for this test data point. And that actually becomes super interpretable and super fast in inference. Here's an example where the ground truth function is, it's just sort of -1 times this dimension, 0 times this dimension, +1 times this dimension. And yeah, you can then, these are the shape functions that come out. There is some noise, so it's not perfect, but you can then look at this and actually just give this directly to someone who would like to understand what the predictions are. All right, there's a new model that came out sort of 1.5 weeks ago, Limix, which is quite nice in that it actually has multiple output heads. In TAPIFN, we had a classification model and a regression model, and they were independently trained. Limix has multiple output heads, one for regression, one for classification, and then also one for infilling values. And it's trained with this masking laws, which allow it to directly output multiple of these masked X values. Final slide in terms of technical stuff on my side. There's lots of extensions that allow us to tackle new types of problems. So there's this extension to data drift that we had at NeurIPS last year, where you basically change the prior to include the possibility of drift. And then, yeah, you can actually make out of distribution predictions much better. Then there's counterfactual reasoning, counterfactual fairness with fair PFN. So there we want to reason about what would the result be if this protected feature here changed. If this person here was, I don't know, male, not female, what would be the probability of them having an accident, for example? This is in some insurance domains, this is actually allowed to discriminate on that, and it's clear, yeah, the females are better drivers, so they should actually get a lower probability of having accidents. But then there's correlation, and in other domains, and actually, right, in Europe, this changed. In Europe, you're not allowed to discriminate on this anymore. So now you need to actually take this out of your data. You need to see what is correlated with being female. Maybe you have the height of the person. And if you have the height of a person, you can, with a high probability already, get the gender. And then you need to sort of take out the impact of this protected attribute on all the correlates. And that is very hard. It's this counterfactual reasoning. And you can't really do it because you don't have counterfactual data. But if you actually can generate hundreds of millions of data sets, where you can generate anything you want, you can actually, in the structural causal model, take out the outgoing edges from the protected attribute, and that protected attribute will not affect anything else. And then you can actually learn to take in the unfair data and predict the fair outputs. And you can do that over hundreds of millions of data sets, and then learn to take in unfair X, unfair Y unfair X test, predict the fair Y test for that with the outgoing edges from the protected attributes cut. And likewise, you can do a similar thing with interventional reasoning. So what would happen if I go and change this variable here to this value? So I like to have this example here. When you want to decide, should I do an operation on this patient? What will be the survival rate? I can't just go in my database and see, like the times I did an operation, they lived this long. The times I didn't do an operation, they lived that long, because there is some confounder there. They had an operation because they were really sick, or there was a reason that they got an operation. It was not a randomized control trial. And if you just have this observational data, then again, you can't do interventional reasoning if you don't have any data about interventional data, interventional variables. But you can meta-learn it. In the meta-learning sense, again, you can generate anything you want. You can generate interventional data, you can generate observed data, and then you can take observed data and make predictions. What if I was to make this intervention? And you can actually then do dramatically better than standard methods. And if you don't do this, then a standard method is systematically biased in making these predictions. If you take a random forest, or if you take a XGBoost, or if you take a TAPPFN, they're all biased. But this do-PFN with this interventional reasoning will not be biased. And so I'm pretty excited about this, because this of course could open a lot of different doors for applications, because in the practice, well, we don't make predictions just for the sake of making predictions, but we actually make predictions in order to change something. Like, for example, all of Bayesian optimization does that. Right? We built this model in order to then actually change some variables, and we actually need to make sure that, we're doing the right types of reasoning there. And that's why I'm pretty excited about that. This is for my last. This is for the demo in the end. You can already look there if you want, but up next is Nick. Thank you. Should we take some questions now? We have a Q&A in the end. We could eat into that.
We have a Q&A, but also
maybe like a couple of minutes now, a couple of minutes after yours, and a couple of minutes join.
Sure.
I just wanted to ask a little more detail about the very last one, the interventional do-PFN. How robust, in your estimation, is it, today, right? Obviously it's state of the art, but is it, something that you think can make really good decisions for, medical patients, stuff like that?
The evaluation is very hard, because you need data where you have observational data and you have randomized control studies. And that is rare. And all the evaluations are on sort of synthetic data. There's actually like 2 parallel papers that do something very similar. There's this causal PFN from layer 6 and another one. They're all submitted to NEURB, so it looks like they might all come in, which is nice. But so it is definitely something, because we use structural causal models in our prior, the causal community was like, oh, this sounds cool, and this is sort of the obvious thing to do with it. And none of them have a good idea how to benchmark this. And so we've been talking to each other and like try to use the best benchmarks, but it's kind of hard. And we do hope that once it's actually out in the open, that then people will come and say, hey, I actually have this problem and I have some data, and then maybe you can start doing some studies in sort of low impact settings where if you're wrong, it doesn't matter so much. I don't know, if you charge someone a cent more or a cent less, maybe that's not so bad. I wouldn't start with, life and death decisions in clinical trials and so on. But it is sort of the right thing from a theoretical perspective. There might be some failure modes and so on. So that's, of course, why we need like very solid empirical studies. But the empirical studies are particularly harsh because of all the confounding and so on.
Thank you.
Small question about time series prediction, do you have to pre-process time series like dtrend or something like that?
Do we have to pre-process?
Time series for TypePFN to work.
Oh, for TypePFN, no, like the pre-processing was really just this featureization. That was it.
Thank you.
Yeah. Anyway, and there's sort of the standard scaler and so on is in there, so a limited amount of pre-processing, but that's already in TypePFN.
Yeah, I would also have a question. So you showed that there are a lot of work who do this pre-processing if the features are too long or the number of rows are too many. Is there an idea to put that into your TypePFN at some point, or are you just like saying, yeah, well, there is other works which already do that?
But you call it pre-processing. I would actually call it post-processing, right? So or you can pre-process before you call TypePFN. But some actually are also building foundation models with this sort of being like happening inside of the model building, and that it's a big space right now. You can do fine-tuning, you can do prompt tuning, you can do you can work with different architectures, you can do a retrieval. And which combinations of these will be best? Sort of a question for the AutoML community. And yeah, I mean, so you can just use a fixed foundation model or a fixed set of foundation models and then figure out, okay, what can I do with them? What is my space of different operators? And there might be a lot in there, but it's not trivial. It's not just a hyperparameter optimization problem. You kind of need to think about, okay, how do these interact and so on. But it would be really nice if we could automate this, because so far this is completely manual.
Thanks for the great talk. I just have a quick technical note because the QR code leads to a Colab that is not accessible. We had this in the previous previous demo. Maybe you need to reshare it.
Good that I showed it, because then I have like 45 minutes while Nick is talking to fix it.
The demo from the GitHub works. Maybe just change to your
Yeah, I changed it though a bit.
Thank you, Frank. You said that you mentioned a couple of times that you can fine-tune TypePFN to your own data set, right? Do you think that this can help where dealing with the very small point sets? Because I've tried to use it for BO as a surrogate, and the prediction was super noisy, super regressive, and I thought maybe if fine-tuning with similar landscapes that I expect, if it helps with at the beginning of the convergence, because we don't have many points.
Yeah, so there's different answers to that. We do have a workshop paper at an ICML workshop where we basically said if there is a small data set and it's very small, then we could actually take the small data set and generate structural causal models such that they actually match the small data, and then continue pre-training on the structural causal models and then apply the resulting TypePFN on the small data set. And it did improve performance a lot. But this is not something you want to do in a VO setting, incremental process. There are already various works on BO with PFNs. Some of them with custom PFNs trained, but also our intern Rosen from MIT, she's actually also in a sort of material science engineering context. She has done it for high-dimensional Bayesian optimization and for one other particular type of Bayesian optimization, and she'd actually just used TypePFN out of the box. So there are existence proofs that sometimes it works, but I'm sure, you know, we also, we look more at scalability, how high can we go? I think we didn't really have data sets that are smaller than 50 data points or so that are very likely in the prior. We could make a TypePFN that's particularly good for like 5 to 50 data points or so. Maybe that actually for Bayesian optimization would be the way to go. And this would actually be cheap, right? Because these trains, like quadratic attention, you don't care for 5 to 50. And we also, I didn't mention this, but we released Nano TypePFN, which is completely open source, including all the architectures. It's 250 lines of code. So far, it's more like an edu TypePFN that's like lets you really understand every single line of code. And when you train it, it's already not bad. We're trying to improve it a bit more. but yeah, especially for small data sets, and this you can train this in like 5 minutes, so not on like large amounts of compute. I mean, also didn't mention this, but it is a foundation model, but as far as foundation models go, it's trained still fairly quickly. The Nature version took 2 weeks on one node with 8 RTX 2080s, which are these 6-year-old gaming cards. So it's still, yeah, took maybe $1,000, but $1,000 is still not something you want to do all the time for your research project. So, all right, should we maybe continue? Thank you. All right.
Yeah, so thanks so much to Frank for that excellent overview of the current state for tabular foundation models and how they're really revolutionizing the tabular field right now. And also thanks all of you for sticking with us here. So I'm Nick Erickson. I'm a creator of AutoGlon, which is an AutoML framework. I'm also a senior applied scientist at AWS AI. And I'm here to talk about how structured foundation models meets AutoML and how we can also support continual evaluation of the state of the art as it basically is rapidly changing in current times with Tabarina. So as Frank already covered, most ML problems don't really use images or text when it comes to, say, industry usage. A lot of it's structured data. And traditionally, machine learning can be pretty tricky in terms of needing to figure out how to do your pre-processing, model training, selection, cross-validation, ensembling, all these different tricks that have now been simplified either by AutoML systems where they automatically incorporate them, or implicitly kind of in the models of these foundation models. So I want to actually go a bit back in time for a little bit and actually talk about the origins of AutoGlon. So the origins of AutoGlon started in 2018 when I was just a software development engineer at Amazon coding Java ETL pipelines and doing nothing related to machine learning. And a internal machine learning grand challenge appeared called the Scott Grand Challenge 2018, which determined if any two products at Amazon.com are duplicates of each other. This is a very important problem because you want to avoid buying multiple copies of the same product in your stores. You want to make sure pricings are consistent, that you're actually the right person, you're actually working with the correct person on selling a given product, right? And so this was a massive problem back then. And so over like, I think 500 to 800 scientists entered this competition. And so we ended up working on this, myself and Alex Shirkov, who's there in the audience. We decided to throw our hat in the ring. Again, we didn't really expect to win or anything. We weren't like professional, applied scientists and stuff, but we wanted to give it a try. And so we ended up going pretty hardcore on it and finding a bunch of different ways of gathering features. We took unit conversion tables from Wikipedia and then put that into regex to filter out what is the total size of a given product. For example, a 12-pack of Coca-Cola 8-ounce, right? You could then convert that to the total size, and then in a different title of the product could just have the size and not say anything about the unit counts and stuff like that, right? And then on top of that, we made a weighted ensemble model inspired by what was happening on Kaggle with like gradient boosting tree models and neural networks and all this stuff, which finally led to the final prediction. And this ended up actually being the first place solution by quite a large margin. That kind of catapulted us into a pretty interesting space because we were in an org that didn't have anyone that was doing machine learning, but actually had a lot of opportunities to apply machine learning. And so we actually got approval from our director to basically form a machine learning team in this org and try to solve the problems of the org and actually productionize this solution. And so with this, we started systemizing code across multiple challenges and basically real use cases that we were working to solve for our org. including like Scott Grant 2018 for item matching, hazardous product classification, determining the root cause of like tickets or issues that come in. And also in 2019, we participated in the next grand challenge, which was shipment cost prediction. An interesting thing with the 2019 challenge is by that time, we'd actually built an AutoML system to like solve these types of problems because no one in the org knew machine learning. So in order for them to use machine learning, we needed to make it simple, right? And that's why we made an AutoML system kind of incorporating all the tricks that we found across these competitions. And when we entered the Scott Grant Challenge 2019, all we did is we ran our AutoML system and submitted, and it won. And so our experience showed that unstructured data sets, properly designed and applied ML framework, likelihood results the top 10%, and in many cases will outperform existing production systems that were built using specialized solutions. And that's really nice because an AutoML system is generally more standardized and maintainable than some customized solution where someone makes it day one, right? They maintain it for a little bit, then they leave the team. And now this becomes this legacy solution that no one truly understands, no one's really maintaining, getting more outdated security vulnerabilities, right? And you need to either live with that or somehow bring someone new in that will repeat the whole process again, right? And make their own customized, specialized thing that then they'll leave the team. So this helps to make it more maintainable as well. Yeah, common mistakes and enables experimentation at a highly accelerated rate. So after the sequence of events, I received a life-changing email. It was from someone named Alexander Smola, who said that he had noticed that we had been working on AutoML with pretty good results and wanted to chat. So who is Alex Smola? Well, he's a VP distinguished scientist at Amazon Web Services in machine learning. And so I was like, I wonder who this guy is. And so I looked him up and I saw his GitHub profile picture. Oh wait, first of all, he had 200,000 citations, basically, one of the most cited researchers in the machine learning field. And this was his GitHub profile picture. And I was like, what am I getting myself into here? But I chatted with him, we met up, and it turns out that he's a really cool guy who's really passionate about open source and pushing the field forward. And he was working on an AutoML system called AutoGluon. Now, Gluon at that time was basically the Keras of MXNet, and MXNet was a deep learning library built by Amazon. Now, AutoGluon's original purpose and idea was to be a hyperparameter tuning wrapper around Gluon models. So like natural language processing models, image models, etc., right? Nothing to do with tabular. But basically, he saw the stuff that we were doing, and then we just were airdropped into the code base, copy pasted the whole thing in, and now we had this, tabular thing, right? And so it was an interesting time. And then I joined in, I believe, October 2019, copy pasted the code in and clicked the release button in December 2019. And then we released the paper. And at this point, actually, this is an old screenshot. We're now at over 1,000 citations. So it's pretty cool. Yeah, so, and basically ever since then, we continued working on it, improving it, iterating on it to, make it more and more widely usable. So AutoGluon today is a Python package you can install via pip. It's fully open source, and it is the current state of the art for AutoML systems, as recently as, say, the AutoML benchmark 2025, where we are statistically significantly outperforming the other AutoML systems. And it's all in just 3 lines of code. After you import the package, you can say predictor equals tabular predictor, specify the label column you want to predict, basically your Y test or your Y, and then you call fit with your training data, and then you get your predictions with predictor.predict, and that's that. right? Now you can specify a bunch of different things here, but this is the bread and butter, right? But the main thing you would want is to say like presets such as best quality, or now we have extreme quality as an example that defines kind of how aggressively are we going for peak accuracy. So some recent results. AutoML has become, or AutoGlon has become the ML community's go-to tool for competitions. AutoGlon was inspired by Kaggle, and I'm glad that now it's being embraced by Kaggle. So it was used by Kaggle competitors to finish in the top 3 in 16 out of 20 live Kaggle competitions in 2024, with an average of 1,500 competitors per competition. So how does it work? So at a high level, we want to maximize diversity of strong models and basically synergize them through ensembling. So we have all of the best gradient boosting models like XGBoost, like 2M Cat Boost. We have a bunch of neural network models from Torch and FastAI, etc. We use things from scikit-learn like random forest, extra trees. Yes, and then we put all of those into a multi-layer stack ensemble. So basically, this is a little bit complicated, so I'm not going to go through the full concept of it, but basically, you train models as normal in here, doing bagging. Basically, you do like cross-validation. And then there's a technique where we can basically take the predictions of these models as features to other models that we then train. And what we actually are kind of creating is a fully connected neural network with a skip connection, where each neuron is an actual full machine learning model trained end to end. Of course, we aren't doing backpropagation here, so we'll fit it layer by layer here. But this ends up being a very, very strong generalized solution to a lot of problems that gets really good results. And if you're more familiar with like LLMs and such, there is kind of an analogy to, say, like mixture of experts, where you have, you know, multiple LLMs making predictions that goes to a judge and stuff like that. So I've talked a lot right now about like AutoML, right? But where does these foundation models come in, right? You know, we've seen like from Frank's slides that TEPFN's actually outperforming AutoGlon. So all this stuff, you know, whatever, all these dependencies, it's all outperformed. And TEPFN does it 5,000 times faster or whatever, right? So what's the point of continuing in this direction, right? Well, I would say the best thing that ever happened to AutoGlon was tabular foundation models. So let's talk about evaluating the state of the art and embracing these things. Tabarina, a living benchmark for machine learning on tabular data. So let's talk about the state of the field and what is considered state of the art, and basically what is pushed in recent like research papers that go over this. So there are very recent papers, such as in 2023, that have been cited hundreds of times at this point, that showcase certain model rankings for how strong certain methods are. And then people will go and cite that paper and then fit their method and show that they're rank 1 on that benchmark and they are state of the art. We've done it again. And it turns out that it's pretty easy to beat these things. I don't need to invent a new method. I'll just use XGBoost. So all we need to do is maybe make the search space not bad, and then fit it correctly, and you beat it. But we can go a step further, because there's something better than holdout. It's called cross-validation and bagging. And now we not only beat everything else there, but we completely destroy them. It's not even close. So if I just implement some method, it doesn't have to be very good, and I do proper 5-fold cross-validation with some hyperparameter tuning, I could say almost anything state of the art. And that's what happened to some extent. Another issue that can happen is that when these benchmarks are created, oftentimes they just kind of take whatever data sets are available from OpenML, throw it in, and try to get a bigger number of data sets than the previous benchmark to basically, you know, say like, this is the biggest benchmark that's ever been created for tabular data, most comprehensive, right? The problem is that there isn't a lot of sanity checking of actually the quality of these data sets and what you're actually throwing in there. A lot of them actually are image data sets converted to tabular format, or they are synthetic, right? Or there's many very similar data sets that are doing the same thing. Or you have data leaks, and certain types of models actually are better at exploiting leaks in data than others, especially in some cases, tree models are very good at it. And that's great and all, but are you really wanting to rank how good methods are based on how well they can exploit a leak in the data? I don't know. So this is a brief rundown of some of the more recent benchmarks over the past like 5 to 10 years. And so the question is, well, we heard about all these problems, right? If only we just fixed all those problems and made one more benchmark, we should be good, right? Not exactly, right? Because benchmarks require continuous updates. What is state of the art today might not be state of the art tomorrow for even a given method. Someone might find a better hyperparameter search space, a better way to leverage the data or to do cross-validation. Maybe you want to do decisions or like temperature scaling, and there's a better temperature scaling algorithm, right? Lots of things can change. And so what we want to be able to do is to drop in new results for a given method when it's able to improve upon what was already there before in the same benchmark. So we need a new benchmark, a living benchmark. This is my good collaborator, Leonard, who is the most insistent on these things. And we aim to end this malpractice. So the team, we come from a variety of different institutions, including AWS, but also like INRIA from Paris, as well as University of Freiburg, Ellis Institute. I'm happy to have Frank along with us as well. Yeah, and so the background here, right? Again, tabular data, we get it. Okay, well, hold on. Okay, so we will make a distinction that we, for now, are going to be focused on IID data, just because thinking about data drift and something, again, is a more complicated topic that muddies the waters of what is actually state of the art. So these are some like nuances. So basically there's several slides I have here where it's kind of just saying like, we're looking at the simplest possible scenarios, but doing them as well as possible initially. And then we will plan to expand that over time as we have a good foundation. So many successful AutoML focus on IID. So what we want to do in Tabarina is find the best models we should integrate into AutoML systems. Not only is a benchmark, a proper benchmark able to articulate the state of the art for individual methods, but it should also be able to tell you how you should build your AutoML system in some way. As well as being able to simulate complex ensemble pipelines, which I'll get into, and meta-learn model portfolios. So we also consider Tabarina to be a research platform for AutoML. So I'll talk about where we are right now with Tabarina version 0.1. It is currently in submission to NeurIPS, so this is very recent work. We hope that it will be accepted and that we'll see you in San Diego, yeah, later this year. So yeah, we want representative models, data sets, and evaluations, and explicit focus. Yeah, so IID data, evaluating peak performance of models, and predictive machine learning for classification and regression. For models, so modeling traditionally has been hard to get right. A lot of the benchmarks, basically, they tried, like XGBoost, CapBoost, MLPs, but the problem is that the search spaces often aren't actually very good. And oftentimes the reasons or justifications for the search spaces have been, well, this prior benchmark that was cited a lot used it, so we'll use it, right? But I think that's a bit risky because again, we've shown that you can actually just have a slightly better search space and just beat whatever is in the benchmark. So instead, we made sure to spend a lot of time refining these search spaces and actually like benchmarking them on those older benchmarks, and then demonstrating basically they significantly outperform the configurations that were there and those other benchmarks. And yeah, so we implement all these methods here. When possible, we will directly work with the authors of the methods for them to inform us of their desired search space. And not just that, but we will actually work with them by running it, showing them the results, and then they actually have opportunities to work with us to actually further refine it and make it better. Yeah. So, yeah, another thing we do is that we ensure that we have 8 inner splits. So basically we do cross-validation with bagging for the methods because this ends up getting you much stronger results in practice. I actually will have a slide comparing them later on. We also fit 200 configurations for each method. So basically 200 iterations of hyperparameter tuning, as well as up to 200 hours of compute budget per task. For data sets, this was a truly intense effort by Leonard Perker and Andre, where they manually went through 1,053 data sets from all of the prior benchmarks and manually curated them and basically looked at if these data sets made sense. And so they have this impressive document, and let's see if I can get this video to play, where they're gonna, so we had written reasons for every single data set as to why or why not they are included. So again, all of that to get to 51 data sets, to give you an idea of how many data sets in these benchmarks in the past were very low quality. Okay, so yeah, data set overview. We kind of go from the small to medium scale data sets, not too much over 100,000. We do plan to go to larger data sets in future though. Yeah, and how about results? So first, for our experimentation, we will run experiments with 30 repeats for data sets with less than 2,500 samples, or 9 times for all other data, basically to have a lot of results to avoid just random chance. And we use the ELO rating system, which we believe is a very stable system for evaluating methods. ELO system is used, for example, in chess to compare if the win rate probabilities of 2 players facing each other. You can actually do the same thing for machine learning models. And we use robust benchmarks. I'm gonna speed through things a little bit. We also use AutoGluon as a reference pipeline. This is basically a sanity check of, right, if your solution is way, way worse than AutoGluon, for example, then perhaps there is some things that you're missing, such as like bagging and cross-validation and et cetera, right, that would boost things. And it also means that if you can beat AutoGluon, that's like a very clear indicator, right, that you have something special going on and it's like a very good model. And we store a bunch of metadata to basically be able to do simulations to see like, what if we did a certain amount of HPO, or what if we ensembled different models ran on a given data set, like different across the model families, we can actually figure that out. So like CapPFN configuration 34 with CapBoost configuration 72, if we ensemble them together, this is what the result would be, right? And then we could simulate that across all the data sets and get that theoretical AutoML system of those 2 configs, that result, right? So this allows us to actually search over candidate AutoML systems, basically. So the results are as follows. This is for the full 51 data sets. Notice that TabPFN, for example, isn't here in this figure. That's because we only include our methods that succeed on all tasks in the main figure here. And TabPFN currently only is ran on less than or equal to 10,000 samples, less than or equal to 500 features, for example. But we can see that, again, as Frank highlighted, these RealMLP and TabM models if you actually ensemble them correctly and like tune them really well, they're actually very, very good. And these are models that are not part of AutoGluon at all. So yeah, evidence that basically these deep learning methods are actually starting to outperform gradient boosting models. Yes. And here is with the TabPFN subset of data sets. So you can see, as in the paper from TabPFN outperforms AutoGluon. Although in this case, this is with the post hoc ensembling logic, right? This isn't necessarily time equalized exactly, right? AutoGluon here is ran for 4 hours. This is like 200 configurations, but it shows the potential of basically these things outperforming. And even like RealMLP and TabM in this scenario also outperforms AutoGluon 1.3. Some additional results. We can also track the run times of these systems, both for inference time and training and validation time. And note that some models, such as TabGPT, even though they train very fast, their inference time is incredibly slow. So it's good to look at both of these things. Talking about holdout and cross-validation, this is what happens if you don't do cross-validation and you just do holdout in your benchmark. The red is holdout ELO. So basically, not only are all your methods way worse, but the ones that are rank 1 in your benchmark actually change dramatically, because certain methods like neural networks actually benefit a lot more from ensembling that comes from bagging than, say, LightGBM, CapBoost, XGBoost, which are already, in a sense, like ensembles. So it's very important to do bagging, and notice that nothing comes close to AutoGluon if you aren't doing that, because AutoGluon is doing bagging for everything, right? And again, with the simulator, right, we can simulate portfolios of models that actually can outperform AutoGluon here or in anything, right, by mixing the families together, basically, in this simulation. So what is the end state of this? So again, this is a good start, but we aren't done. This is a living benchmark. So new methods keep coming out. Improvements to existing methods mean they should be reevaluated. And with new results comes new opportunities to improve AutoML systems. So I need to go quite fast here, but AutoGluon 1.4 is the next release of AutoGluon. It released in, I believe, August or July. And it is just a fixed portfolio of 21 model configs. We train 21 model configs in order, we bag them, we do a weighted ensemble of their predictions, and we return the result. That's the whole system, basically. And it's the same 21 model configs with the same hyperparameters for every task. It's 3 LightGBMs, 5 CapBoost, 2 XGBoost, 6 TabM models, 3 TabPFNs, 1 Tabical, and 1 Mitra model. And you can find the exact hyperparameters for everything here. And so this completely shatters the state of the art. It's 300 ELO higher than AutoGluon 1.3. And it has, like, I think an 88% win rate versus AutoGluon 1.3. So basically, right, tabular foundation models is not the end of AutoML. It's just the beginning. Now we have this really powerful, really fast model that we can put at the start of our portfolios to kickstart the process. And then you can find models that maximally synergize with them to get even better results. And this isn't even the highest that it can go. This is just what I did that was like a reasonable start from these results. But like it can be pushed even further by adding more configurations than just 21 models, or by doing stack ensembling with them and all this other stuff. And speaking of, again, a living benchmark, we also have new models coming in, such as Mitra, which is a tabular foundation developed by my team at Amazon. And it's pre-trained exclusively on synthetic data, just like TabPFN. And it particularly has strong fine-tuning capability to enhance performance. Basically, we pre-trained it in a fashion to maximize the fine-tuning performance rather than the in-context learning performance. It's natively integrated into AutoGluon, and it was the #1 trending model on Hugging Face for tabular classification regression. Someone downloaded over 1 million times in under a month. I don't know who, but. And then on top of that, just last week, again, as Frank said, Limix came out, brand new tabular FM, shows promising SEL results. Does it work? Well, we can find out very quickly. We just add it to Tab Arena, run it, and we have our result, right? And so this is the current status basically of the leaderboard right now. Again, continually updating, working with the authors to push things like we have TabPFN v2, like real TabPFN, right? That's even better than that. We have an improved version of real MLP in the pipeline that's like 80 ELOs higher than what it currently is, right? This is a continuing benchmark process that evolves over time and keeps improving, and that's the goal. So, yeah, we have Pareto frontiers as well. If you care about like training time and inference time, we can see it's like the full AutoML system, right? But then you have like the fine-tuned foundation model, and then you have the, in-context learning foundation model. It makes a lot of sense, kind of like what's along this Pareto frontier. And we can build AutoML systems that can basically give you any point of this Pareto frontier out of the box, as long as you explain what you want in terms of constraints. Yeah, so I'm gonna need to just go through, but basically, yeah, we got a lot of things coming in, and we love benchmarking, we love AutoML, we love ensembling, and we hope that we can support the community to accelerate our modeling efforts. Thank you. So with that, I'll take a couple questions, and then Frank can finish off with the demo. Yeah.
Thanks for the great talk. The question I have is, how did you end up with the portfolio? How was the process of getting there?
Yeah, so this is something that I talked about in detail, I think 2 years ago at AutoML conference with the Tab Repo paper. So I would recommend looking at the Tab Repo paper. Basically, Tab Arena is Tab Repo 2.0. It's built upon the same code base. And with that, so we keep all the predictions of the prediction probabilities of the validation and test predictions for every model we fit. And so we can actually simulate a portfolio, basically. And so we do a greedy portfolio building process where we select the single best model across all tasks, and then we select the single best complementary model. And the way that we avoid overfitting here is basically we can do leave one data set out to verify that this strategy doesn't lead to overfitting. And basically we optimize the hell out of everything. So it uses Ray, and we wrote all of the evaluation metrics in C custom, so that they're like over 100 times faster than what you get in scikit-learn. And then we can just process fitting like hundreds of millions of weighted ensemble models in under an hour to basically brute force, in a sense, what is the state of the art given all of the possible models results that we have, right? And so if anyone submits a new result, we just rerun this pipeline with the new results included, and then we will find the new state-of-the-art portfolio, right? Yeah, thank you. All right.
Let me ask you a question too. Yeah, just to follow up. Just to follow up to this question. So if you optimize this on a relatively small set of data sets, like 51 in Tab Arena, there's this ongoing debate. I'm not sure if 51 is the best, or if we should have a larger set that maybe is slightly worse quality. What are your thoughts about that?
Yeah, I actually do think that having a larger set that's slightly worse quality would end up being better for the portfolio, like the meta learning process, right? I just think large amounts of data sets is just so critical for this kind of stuff. We do try to guard against it by having a lot more like repeats of the runs than we did in, say, like Tab Repo, where we only had 3. Here we have between 9 to 30. But yeah, I do think more data sets is generally better, but we're gonna have to, figure out what's the best mix there. I think there's still more work to be done. I think it is the right call to like try to have really good data sets to start with, and then you can kind of compare, okay, if we add slightly worse data sets, does that end up generalizing to the good data sets if we like build things, right? Yeah.
Cool. Any more questions? Not the case, then I'll do a quick demo and there will be more chances for questions. never do a live demo. Let's see. All right. So this should now work. The QR code I would use. You can also go to the GitHub.
Currently, we just see.
Oh, interesting. Why is this?
Worst case, you could try it.
Where are we?
You try closing it, maybe, like the PowerPoint. Here we go. Oh, I see complaints.
It's here. Good. All right. Yeah, the QR code would be better than going to the GitHub because I did change some things. Great, my runtime is disconnected. That's a very good start. All right, then I will go through, try to go through live.
Couldn't show QR.
Yes. Actually, let me get this started, and then I will. Go. Okay. Okay. Yeah, and as always in Colab, you need to restart the session after the first cell.
You might also want to zoom in a bit so that people can see the text.
Point. Okay, have this restarted. All right. So yeah, in the beginning, so this Colab is just a sort of condensed version of the Colab that we have online because some things, some cells take a little bit too much time. And yeah, so it just walks through how to use TopBFN instead of like with the scikit-learn interface, just a really standard interface, and then showing it on a few data sets. Okay, so this first cell was just a installation. Then the next cell, yeah, I think that's just some standard imports that should be pretty fast. Concerned that it's not that fast, good. All right, and then there's a step where you need to select the backend. So we do provide an API version where you can actually send the data to us. We run it on our GPUs, you get the results. So this is particularly useful if you don't have GPUs. Do not send private data there because we do lock that data because we do want to see what is being used for. If you write local, then it doesn't send any data, but here it's local. Local means in this Colab has a GPU, so it's going to be fast. Of course, you have a limit on Colab GPU, but you can just run this on your own GPU. If you don't have a GPU and if you have some data that you would publish anyways, be welcome to use our compute. And then, yeah, as Nick and everyone else, we're trying to collect public data sets. We actually had, before my time at Prior Labs with Joachim Machoren, we were looking to get modern data sets into AutoML, and we had this Twitter campaign where we reached out and said, hey, please submit data sets. And there's a lot of tweets, and how many data sets did we get? 0, exactly 0. With this, people are uploading all kinds of interesting scientific data sets and so on, because it's just easy. Again, don't upload any personal data, because it would be a lot of headache for us to remove that. All right, yeah, so this just loads some data here. In this case, it's Parkinson data set from AutoML. It's pretty small, so we can iterate pretty quickly on this. Just displace this a bit. There's alternative data sets you could try. Then, yeah, it just splits it into X-train, X-test, Y-train, Y-test, and fits a TopBFN classifier. So that's what's happened here. And then you can also compare this to other methods. So here's a random forest, an XGBoost, a cut boost. and it's going to run threefold cross-validation, and yeah, the defaults are roughly the same for all of them in terms of compute time. And here, well, this is ROC AFC, but you can also look at other metrics. Then there is regression. So here is loading Boston housing. And again, there's alternative data sets you could use. You do your data splitting, do the computation, get your RMSE. And then again, you can do comparison. Comparison, you should always do CV, as we heard. We only do threefold CV here because we don't want to wait too long. But yeah, then yeah, so here we're looking at variance explained R2. And then model interpretability. Here we're getting to the point where it does take a little bit of time. Maybe I shouldn't have clicked this one because that actually took a little bit too long earlier for being in the live demo. Maybe I'll switch to this other. No, but the runtime there is broken. So this, yeah, we can wait it out, or we can actually do this later. It's it doesn't depend sequentially. So you can also look at, so SHAP is slow because it's doing a lot of predictions. And actually we would be interested in sort of faster approximations of SHAP, particularly also for TopPFN. But let me go through the fast things first. So you can look at embeddings here. Yeah, so you can do visualizations of different embeddings. And here, for example, you see the TopPFN embeddings in an unsupervised manner. When we actually post hoc know what the classes are, it actually can tell the classes apart already. Then you can do feature selection, which is, yeah, pretty simple. It will run for a while and then tell you a few features that are the most important ones. But that, yeah, it is a very, very simple forward selection. I hope that is not too slow. That was also a little slow earlier. Maybe I'll also push it to the back. But then decision boundaries, this is interesting to actually look at. So here we have some data that's, yeah, these circular patterns, which is something that for traditional methods is sort of a little tricky. Random forests are very noisy here, very axis aligned, and TopPFN, this is a typical example sort of for feature preprocessing. If you do a good feature preprocessing, you just say what distance from this point here, and then it's a linear prediction, but actually not quite linear, but then it's just binning, and you could do another warping of your data, and then it would be linear. But TopPFN doesn't know any of that, but somehow it does it in some of its layers. Yeah, then sine curve fitting. So you have this curve, like how would you fit this? Well, how will trees fit it? We saw that earlier, more like this, just very locally, and TopPFN just interpolates more. Right, then uncertainty quantification is here. I think this was just a plotting, sort of plotting functions. And then we have the predictions already. We just need to plot them now. And yeah, so you see there's a hole in the data, and the uncertainty here is small. Here there's larger uncertainty in the data, as we see, and in between it predicts a growing uncertainty. All right. With that, let me run the other methods that we skipped while we're taking questions.
I have a question.